All right, today we're going to break down one of the most fundamental building blocks in all of electronics, the series RLC circuit. We'll look at each component, see how they behave together, and really uncover why they're so critical in the technology we use every day. It seems like magic, right? But it all comes down to the precise and, honestly, elegant interaction between three very basic electronic components. We're going to explore the core principle that makes this kind of frequency selection possible. Okay, so first things first, let's introduce the three key players in our circuit. We've got the resistor, the inductor, and the capacitor. So in a series RLC circuit, just like you see here in the diagram, these three components are all connected end-to-end in a single loop. And what's so important about that? Well, it means the exact same current has to flow through each one of them at any given moment. This is a really foundational concept that everything else we talk about is going to build on. Now, here's where things get really interesting. Each of these components has a very different relationship with the alternating current. For the resistor, it's simple. The voltage and current are perfectly in sync. We call that being in phase. But the inductor and capacitor, they each introduce a time delay, or what we call a phase shift. The inductor's voltage actually leads the current by 90 degrees, and the capacitor's voltage lags behind the current by 90 degrees. So you see they're in direct opposition to each other. And that opposition is the secret to this whole circuit's special behavior. So with that in mind, let's dig into how their combined opposition to the current is actually calculated. We call this property impedance. You can think of impedance, and we use the letter Z for it, as basically the AC version of resistance. But here's the catch. Unlike simple resistance, impedance isn't some fixed value. It actually changes depending on the frequency of the AC signal running through the circuit. But here's the thing, you can't just add these oppositions up like you would with regular numbers. It's what we call a vector sum, and the best way to visualize it is with this impedance triangle. The resistance, R, makes up the horizontal base, and the net reactance, that's the combined effect of the inductor and capacitor, forms the vertical side. And that brings us to the formula for finding the total impedance. It's the square root of R squared plus the square of the difference between inductive reactance, XL, and capacitive reactance, XC. Now, that term reactance is just the opposition from inductors and capacitors. And I want you to pay close attention to the fact that we subtract them. This is the math showing us their opposing effects in action. All right, let's make this real with an example. So let's say we have these component values and a frequency of 50 Hertz. First, we calculate the inductive reactance, XL, which comes out to 47.13 ohms. Then we do the same for the capacitive reactance, XC, and get 31.83 ohms. And finally, we just plug all those numbers into our impedance formula, and we get a total impedance of 19.4 ohms. So this whole opposition thing between the inductor and capacitor, it's not just some weird electrical quirk. It actually leads to this really powerful and unique phenomenon that we call resonance. So you've got to ask, right? What happens at that one perfect frequency where these two opposing forces, these two reactances, are perfectly balanced? This is the central operating principle of the whole circuit. That's exactly what we call resonance. It's the one specific frequency where the inductive reactance is exactly equal to the capacitive reactance. And since their effects are perfectly opposite, 180 degrees out of phase, they completely cancel each other out. And this graph shows you exactly what happens. At that special resonant frequency, the XL minus XC part of our impedance formula becomes 0. What does that mean? It means the circuit's total impedance, Z, just plummets to its absolute minimum value. And that minimum value is just the plain old resistance, R. So let's think back to Ohm's law, but for AC circuits. Current equals voltage divided by impedance. It's a simple inverse relationship. If the impedance, Z, is at its absolute minimum, then it logically follows that the current, I, has to be at its absolute maximum. And this ability to let the most current flow at one very specific frequency, well, that's the key to everything. So why does all this theory matter? Let's take a look at how this principle of resonance is actually used in the technology all around us. This unique ability to respond to frequency is what makes these RLC circuits so incredibly useful. They're essential parts in a huge variety of systems, everything from communications to power electronics. So let's go back to our first question about the radio. A radio receiver uses an RLC circuit as its tuner. When you turn that dial, what you're actually doing is changing the capacitor. This changes the circuit's resonant frequency. When you get that frequency to match the carrier frequency of a station you want to listen to, the current for that signal is maximized, so it gets amplified, while all the other station signals are basically ignored. And it's the exact same idea behind what we call band pass filters. You design the circuit to have its resonant frequency right in the middle of a range or a band of frequencies that you care about. Frequencies inside that band get to pass through with very little opposition, while frequencies that are too high or too low are blocked by high impedance. It's absolutely fundamental for signal processing. Really, this quote from Keysight just hits the nail on the head. Their ability to resonate to select one frequency and reject all others makes them a true cornerstone of modern electronics. They are simply indispensable. Once you understand the principle, you start seeing it everywhere. From the stable clock signals that run your computer to the systems that provide clean power to your devices. The principles of RLC resonance are constantly at work, quietly and perfectly tuning the signals that power our world.